Hello, and welcome to Group 10 System Engineering Group Project presentation. My name is Alex Siegel, and I, along with my group members Gavin Garland, Lauren Hall, and Ananth Reddy, will be proposing a concept for a low-cost solar system confined configurable surface explorer. There are a number of common issues that we are addressing with this proposal. One of these is that a very small number of celestial bodies have ever been physically explored. A number of orbiting probes have been sent to various locations, but these can only determine a finite set of qualities about the body, and even then a lot of data conclusions have to be drawn through extensive assumptions. In addition, missions that actually do go to body surfaces are extremely specialized to the atmospheric conditions, weather patterns, geography, and much more. Finally, current surface exploration missions are expensive, including little to no intention of fast return time, and putting a lot of weight on a single mission. So what we're really trying to capture with this proposal is to create a rover that can be used to study any celestial body within our solar system. The rover will also be modular to allow for an array of scientific instruments to be used. And then this is important because this technology will allow for more space exploration at a lower cost and pave the way for human exploration of our solar system. We determined our stakeholders based on level of potential involvement with the project, as well as those that might be impacted by the results. These include, but are not limited to, NASA, which is the ideal host of the project, the US government, which would be involved in the permits and verification processes within the project, the scientific community, which would potentially develop extension projects in the future, astronauts, which would be the predecessors to our explorer, since surface explorers are precursors to human exploration, and finally, the general public, which would be inspired for future generations. The needs, goals, and objectives of this project can be boiled down into two main points. Create an inexpensive modular surface explorer that can easily be adapted to meet the needs of any mission, and increase the quantity and quality of scientific data that can be gathered within our solar system. For our concept of operations, we attempted to encompass every possible scenario that the Surface Explorer may be physically put in, providing an outline of the end goal functionality of the system. This activity diagram displays a number of possible routes that may be taken by the Explorer in its operation. Using logic and comparison gates, we were able to develop a multi-dimensional model of situations, whose choices are determined by the system constraints and environment. As an example, the system starts by receiving target coordinates from some external ground station. While autonomously navigating for waypoints and observing obstacles, it shall hold the capability of obstacle avoidance or waypoint reconfiguration. Once at the destination, it can perform the specified task, relay results, and then await further instructions. As a better visual aid, this is situationally what the operations may look like. From our ConOps, we were able to develop a set of top-level requirements for our Surface Explorer. A summary of the goals of these requirements is as follows. The system shall be relatively small in size in comparison to past systems with a mass not exceeding 50 kilograms. As stated earlier, the system shall be inexpensive with a base cost under $10 million. The system shall be fully autonomous but with manual override capability. The system shall be very modular with a sort of snap-fit capability when it comes to optional subsystems. The system shall be operational in a specific target environment conditions. The system shall have power generation and thermal regulation units. And finally, the system shall be capable of communication with ground stations, relay stations, or other surface explorers. So in terms of how the requirements were organized, we developed a block diagram that detailed each top-level requirement and divided them into three categories. Our functional requirements cover what the Surface Explorer must be able to do. We determined that the top levels for this section are navigation, ground communication, and instrumentation. Our constraint requirements laid out the physical limits that specific subsystems would have. These were divided into mass, unit usage, operation time, operating temperatures, and total cost. Finally, the performance requirements of the Explorer show the quality and quantity of tasks that must be able to be completed. The top levels here consist of power storage, operational lighting conditions, structural makeup, thermal regulation, transversible inclinations, low gravity functionality, and obstacle maneuverability. Ananth will now go into some relevant concepts that aided in our design.
So to help with the design of our rover, we need to take note of a few similar concepts. So first off, we have the NASA Mars rovers. So pretty much they act as the baseline for most planetary explorers. So in their case, Mars. So next up, we have the Yutu rover from the Chinese Space Agency. So it's a little bit different. It's a lunar rover, but what differentiates itself is that it's small. So it pretty much has small dimensions as well as a low mass, which is one of the primary requirements we have for our planetary explorer. And lastly is the Hyundai Elevate, as you can see a concept rendering in the below image. And yeah, it's a little bit strange. It's practically a walking car, but as we'll discuss shortly in the architecture section of how our actual Explorer will look like, you'll see why we chose this option. So we then created a functional decomposition for our rover. So the functional decomposition pretty much just notes what are the main functions or primary objectives that we want the actual rover to do. So it was split up into 4 different sections based off of the top level requirements that we defined. So pretty much they're navigate autonomously, operate in variable environments, communicate with ground station, and perform science tasks. So those are the 4 main functions, and as you can see, they're decomposed into sub-functions, and in some cases sub-sub-functions. So for example, in operate in variable environments, you can see all these sub-functions: extreme temperature, low gravity, no sunlight, extreme radiation, and during steep inclination are just some examples of variable environments. So based off of our functional analysis and top-level requirements, we were able to come up with a general physical decomposition or structure of our planetary explorer. So the planetary explorer is decomposed into various subsystems, so communication, power, thermal, instrumentation, mechanical, control, and navigation. And each of these subsystems have their own respective system elements. So even though we defined the top-level requirements already, we actually need to flow those down to the subsystem level. So for our 7 subsystems, we need to define general subsystem level requirements for each of them. And since we have 7 of them, we are only going to talk about a few of the primary ones. So for example, the power subsystem has 4 subsystem level requirements. So we have one for battery capacity, one for power consumption, one for the energy source, which we'll actually talk about in the architecture section, as well as the power storage and how we want to configure it. So next up is the navigation subsystem, which is composed of 2 subsystem level requirements. So the first one is for imaging. So of course we want the rover to have a pretty good sense of its surroundings in case, it needs to maneuver a potential obstacle. And next up we have one for traversing distance, which basically states that it should be able to traverse 100 meters of its environment per Earth day. So we want the rover to obviously, reach the scientific area of interest in a reasonable amount of time. So lastly, we have the communication subsystem, and as you can see, it has quite a few requirements as it is extremely important. So reading from top to bottom, it basically reads, at what distances should the rover be able to communicate, how regular should the communications be, what should actually be included in the communication information, how long should the communications be, how much allotted time does the rover have, and in case there are many other rovers in the area, the rover should be able to act as a communication relay with each other. So next up, Lauren will talk about the system interfaces, as well as the alternative architecture options for our system, as well as the preliminary trade study analysis.
Thank you so much for that introduction. Shown here is the interfacing subsystems, starting with our scientific hardware, our central processing unit, which controls the internal communication and acts like an instruction hub for the Surface Explorer. Next, we have our navigation subsystem, our thermal regulatory system, our communications, and it is primarily external communications, and we can see that over here in this picture where it's sending out a communication outside of the Surface Explorer back to Earth to the ground station. Our power subsystem supplies the power for all power-using components, and we can see an example of that here. This is a multi-mission radioisotope thermal generator, or MMRTG, and it's the one we use in our Surface Explorer. Here is our N-squared diagram, and for an N-squared diagram, if it's coming out the right or out the left, it's an output. If it's coming in from the top or in from the bottom, it's an input. And if it's outside of this red dotted line and it's coming in, it's an external input. If it's coming out, it's an external output. So we can see here that our Surface Explorer is getting an input from the ground station communications. It's going into our communications subsystem and is then being processed by our CPU. And our CPU then tells all the other subsystems what information they need from that communication. Our thermoregulatory system sends heat regulation to all the different subsystems, and our power subsystem sends power to all the other subsystems. And our communication subsystem will export the data collected and processed by the scientific hardware back to the ground station. Here's our morphological matrix. We decided to go with a sheet and support, which is a flat body rover. And we went with aluminum because it's the lowest cost and highest durability of all the materials. We decided to go with metal mesh wheels because it's the highest operational mobility for off-roading capabilities, and it's the most durable of the four. For power, we went with nuclear MMRTG because the other options just weren't feasible for the possible bodies that we will have to explore. We decided to go with a transmission relay network to save costs because it's going ahead and use the entities in space to relay our transmissions. For navigation, we went with an internal guidance system because it's the cheapest of the four. For system controls, we went with a single CPU rather than a CPU network. For scientific operation, or where the scientific hardware is located, we decided with instruments on top because specific instruments have to be on the top, so we just went ahead and put them all there. For thermal regulation, we decided to use the power source because the MMRTG already produces heat. The trade study we chose is wheeled versus tracked vehicle study. This was done by the Army, and it was accessed through the Defense Technical Information Center. And a tactical high is in high operation mobility. It's 6% off-road and 40% on-road. So to have a tactical high, vehicles up to 10 tons need to have wheels. Vehicles over 20 tons should have tracks, and this is how they get the most traction and the highest mobility in the off-roading terrain. Because our vehicle is below 50 kilograms, it's much smaller than 10 tons, we decided to go with wheels because it needs to have high off-roading capabilities. Okay, and up next is Gavin.
Thanks, Lauren. I'm going to be talking a bit about what our rover will look like. Our rover has the dimensions of 35 centimeters by 70 centimeters by 55 centimeters. This puts it on the same scale as the Sojourner NASA rover. The body of the rover is primarily made of aluminum in order to reduce weight and cost. We have an estimate of the total mass of our rover to be about 39 kilograms. The rover will have a four-wheel system, each consisting of spring metal tires which can absorb impacts. Each system will also have an active suspension. This will allow it to pivot and shorten and lengthen so that it can avoid obstacles and traverse over difficult terrain. The rover has a flat top, navigational sensors, and universal attachment points. Each of these attachment points will be modular and has connections for both power and mounting. In low gravity, the rover will be able to secure itself to the ground. All of this, we estimate, will cost about $9.3 million. Here we have a mock-up of our rover. On the left, you can see the rover in its expanded form with its communications deployed and wheels ready to traverse the surface. On the right, the rover is completely folded up in order to make a smaller footprint so it is easier and cheaper to launch. Some interesting features of our rover include its modular mounting system on the top, which allows for a wide variety of scientific instruments to fit a wide mission criteria. The data from these instruments can be autonomously collected and sent back to Earth. Because of the metal spring tires on our rover, this allows for increased durability and longevity of the tires, allowing for increased mission time. The active suspension system allows the rover to easily maneuver around and over any obstacle which it may face. Our rover is designed for a wide variety of climates, and using its thermal regulation system, it can fit almost any mission that we would need within our solar system. Finally, the rover is powered by a radioisotope thermoelectric generator, which can operate on any surface, regardless if there is sun shining or not. We believe our rover is a great concept because of its small size, low cost, modular design, and active suspension system, which will allow for cheap and quick manufacturing, as well as great maneuverability on any celestial body within our solar system. This rover will help pave the way for future human exploration around our solar system and will drastically increase the amount of science that can be done. We hope that you enjoyed our presentation, and thank you very much for listening.